Good afternoon. My name is Jason Weber. I'm the Vice President of Product at Veracity Industrial Networks. Welcome to our monthly open product demo. And the way this works is we just created sort of a low pressure, low stress environment to see how the product works. It goes a little bit less than 45 minutes. Carly will be monitoring the chat, and that's the easiest way to ask a question, and she can interrupt me at an appropriate time to ask questions. Otherwise, we will have a full Q&A at the end of the session. I also will start out in a presentation, and then I'll jump over to the product and do a little bit of a demonstration there. Most of this will be in the presentation because it's just a little easier to get across what we do that way. So without further ado, since it's a few minutes after the hour, I will get started. So thank you for joining us and spending a little of your time with us. So back around the year 2000, we had some very popular things that were available. If you were traveling for work at all, you know that every car that you rented at a rental place was a Ford Taurus. Actually, I looked it up. There was, it was in the double digits of millions of these that were produced. Flip phones were all the rage. The iPod was in its heyday. And the really hot desktop processor was a Pentium 3 with 128 megs of RAM and 20 gigs of hard drive. And that is when plant floor Ethernet was introduced. Profinet, Ethernet IP, Modbus TCP all came about right about then. And a network 20 years ago was a simple thing, an OT network, that is. There was an air gap typically between the IT and the OT network. There were just a few devices that were critical that were on there, generally PLCs and HMIs that were attached. And there wasn't much to it, which made it relatively safe and obscure, and it was difficult for cyber criminals, and there weren't a lot of cyber criminals back then attacking the OT space. Since then, things have changed. Things have gotten a lot more complex, and there's a lot of tools that have been added on to do that. So what we have found is that pretty much all OT organizations struggle to effectively manage and secure their networks. This is a completely fictitious, made up, non-scientifically backed, but backed plenty by intuition statistic, just so you know. That's why there's no reference. But most of the current approaches to managing and securing OT networks are based on IT tools. And these IT network management tools are really designed to manage IT networks, and they are not focused on the realities of an OT network. The fact that in OT networks, production is the most important thing. Downtime is not something that's really acceptable. You can't pull a server down at 3 a.m. for 30 minutes to do an upgrade and just sort of pray that it works. There are proprietary stacks by companies, and the difficulty with that is that in an OT network there are many different vendors. There are many different machines. There's many different pieces of equipment from different vendors, and a single stack just isn't scalable to the whole network. There are tools that have been added on the cybersecurity side of things, which are intrusion detection software, which are great at telling you after somebody has gotten in your network. So maybe it's there for a half an hour. Somebody can do a lot of damage in a half an hour. They're not focused on hardening the network. They are an important part of a defense in depth strategy, so don't forget that. So a network today, and this is a drastic simplification of it just to make it so it's something that's readable, because a lot of the network diagrams we've seen of today are they just look like spaghetti thrown on a wall. But the reality is there's a lot more equipment now. There's a lot more vendors, there's a lot of pieces, there's a lot more databases and data flowing that is required. And the tools that are being used to manage it, such as virtual LANs or access control lists, or just even having spanning tree protocol to make sure that you don't get loopbacks. These things all are incredibly complex. You've got multiple management tools. If you just happen to have multiple switch vendors there and you want to manage switches with their tools, there's so much to do, and you need experts on your plant floor basically nonstop, depending on the size of your installation, in order to keep things running smoothly. Holy cow, if you have a bunch of remote installations that don't have any people there to manage them, you've got real problems. But all of these overlays are, they're great when they're first installed, but the thing that we've really discovered is that over time they deteriorate. You've got segments in your network. You've got control of who can go to what, but the moment that production goes down at 3M, that stuff goes out the window and people start circumventing things just to get stuff back up and running. Also, with some of this stuff, you've got problems like, what if I unplug a device and I accidentally plug it into what I thought was the same port on a switch, and now we're on a different VLAN and it's not communicating? What happens if I get a loopback? We were talking to a food customer and they had a plant taken down for 5 hours by a loopback. This is not expandable. And so what if we said there was a better way? What if we said you could take your network with all the different devices you have on it from all the different vendors and all the data that you want to pass around it and remove all of that complexity, remove all of the pieces that are there that are from IT tools and traditional networking in order to make this a simpler thing. And that's what we do at Veracity Industrial Networks. So who are we? And I'll get into how all this works as we move forward. Veracity Industrial Networks, we have a product called the OT Network Controller. It was introduced about 4 years ago, and we've taken something called software-defined networking and we've applied it to the plant floor. So a little history on software-defined networking. Over a decade ago, clouds were starting to really grow and servers were starting to, server farms, things like that were starting to grow. And traditional networking tools were not sustainable and not tenable to run those things. In a cloud environment, if a server goes down, you have to be able to just take it out. They actually have pods of servers that they replace periodically. And all they do is they drop a new pod in there and they hook up network, power, and air conditioning. And it just self-configures in there. And that's not possible with the traditional tools. So software-defined networking was born. And it essentially centrally manages all the traffic and all the switches from a single piece of software. Within our application of it, we have created a deny by default network. So no traffic occurs on the network without permission from our controller. And we manage all of the communications on an endpoint to endpoint or device to device basis. And what's not written up here is we present it in a very OT friendly format. So what this gives you is it really simplifies the administration of your network, much faster line startup. You have a micro segmented network. People talk about segmentation and defense in depth or zones and conduits if you're looking at 62443. But essentially, we microsegment it on a device to device basis and by communication protocol. This lowers your operating costs. This reduces your downtime because a lot of the traditional things like those loopbacks and misconfigured VLANs go away on an SDN network. Every device communicating on the network is visible to you, so you see everything. And it's just the next generation of networking. So now that I've talked about motherhood and apple pie and a little bit of a history lesson, let's talk about how this works. So we have a network here. This is a network with 4 switches and, a dozen or so endpoints. And by default, as I said, no traffic passes on this network without permission from the server. And so in this instance, I want the PLC in the lower left corner to be able to speak to the SCADA system on the upper right corner and via Ethernet IP. I create a rule in the network or in the network controller and it does the rest. It talks to the switches, it sets up what we call flows between them so the data can flow and everything starts working. If for some reason that wire breaks, it's disconnected, somebody drives a forklift over it, something like that, we will find the next best path and automatically reroute that flow of information. If you move that PLC to a different port or even to a whole different switch, we will identify its new location. We'll of course log that this happened, but we'll reflow the communication again. So this is a self-healing network. If you go into a closet with a network in it and you unplug something and you plug it into a different port, it doesn't matter anymore if you make that mistake. We will find it, we will reroute it. So one level lower now, how does this actually work? So the first time a switch sees traffic, so in this case, the PLC and the HMI want to talk via Ethernet IP. The first time it sees it, it queries the controller. What do I do with this? And the controller says, well, I've got a rule for that. It's okay, pass it. And it'll tell it to pass it. In this case, just through the switch, through multiple switches, it doesn't matter, we'll take care of it. The next time the switch sees the same traffic, it knows, it remembers. I already know that this is okay, I keep passing it. This has a number of benefits. First of all is speed, because we're not asking the controller every single packet what to do with it. But what this really does is it gives you a layer of resiliency of the network. If the controller happens to go away, the network keeps running. And so this really gives us a very resilient network. One of the things that I didn't expect when I first started here 2.5 years ago, but have learned now, is the reality is the connection between the network and the rest of the controller and the rest of the network goes away somewhat regularly. And I was surprised by that, but it does happen. But the network can continue to run when this occurs. And so we also have an option for redundant controller, but for most customers, just the redundancy between the controller and the switches is enough. If you happen to have a bad actor or an employee or a device that hasn't been communicating on this network before, or has been communicating by different protocols, or is being put in there by an OEM that wants to put a cellular motor on their machine so that they can remotely monitor it. The first time we see the traffic on that switch, the switch asks the controller what to do with it, and the controller says, don't do anything with it, block it. It stops at the port. It doesn't get through. It is logged. It is now something that you can deal with. You can either look at it and say, this isn't something that we want, or you can say, yeah, this is a legitimate request, and you can allow the communication to occur. This is the nice thing about this is this also has the benefit of cleaning up your network. We have seen lots of extraneous traffic on networks is always there. We don't allow any of it through there. We have seen multicast traffic that is polluting the network. We've seen IT devices pinging into the OT network for some reason. We've seen DLR beacons get out of the ring and start making a mess of the rest of the network. All that's blocked. It cleans it up. We've had customers that wanted to upgrade to a faster network. They put our stuff in there and all of their throughput issues went away. So it really does help with a lot of things, including stopping bad actors from getting into your network. The next two slides are about how we take and add the Veracity OT Network Controller to an existing network. The first method that we have is something called learning mode. And so what this is, as I said, the switches, when they see traffic they don't know, they query the controller what to do. In learning mode, the default is all traffic passes through the switch. And you can put an entire network into learning mode or individual switches, but all traffic passes through it. And as we see new traffic, we generate rules, learned rules for that traffic. And so once you've had it in learning mode for however long you think it is to see the majority of the traffic, an hour, 2 hours, something like that, you take it back, you put it into operation mode, and then you go in and audit those rules. And the operational mode is a secured network mode, but you go in and audit, you clean up all the junk that you don't want, you organize everything. And once you have done that, you have very quickly taken a non-SDN network and moved it over and created all the SDN rules around it. Once you're done with that, you put it into a mode called system generated drop rules, and any traffic that it sees from that point, it tells the switch just to drop it and log it so that it doesn't continue to query the controller as you see it. And so this is a very fast way of generating all the rules in there. Now let's talk a little bit about the hardware. Within an SDN network, you need SDN enabled switches, and not all switches are SDN enabled. That's just the reality of it. We use a protocol called OpenFlow, and OpenFlow is managed by the Open Networking Foundation. It is used by a number of large cloud service providers, but it is a tool that you must have on your switch. And there are some major switch suppliers that have that. A couple of our partners, Schweitzer Engineering Labs and Dynex, both have very nice SDN capable switches. Allied Telesys is another one, and even some of the Cisco switches. So the distribution switch that we see the most often is the Catalyst 9300, 9400 series. Those can be activated in open flow mode. And once you put them in open flow mode, all of the great stuff that I have talked about since the beginning is all available to you. If, however, you have a hybrid network, you've got some SDN enabled switches and you've got some what we refer to as legacy switches, either managed or unmanaged. Realistically, there's going to be unmanaged switches in cabinets that are never going to get touched until they are panels until they are dead. And that's okay. We've spent a lot of time working in this hybrid space. And so if you have one of those catalyst switches, for instance, you put in open flow mode and every bit of packets that goes through that switch is now under our control. It's managed by us. And just by taking that distribution switch and putting it into open flow mode in our controller, you've essentially segmented your network for way less money and a lot less effort than you would have in a traditional network segmentation project. If you have switches that are capable of software-defined networking or you swap into it, everything that passes through them, is connected to them, has all of the capabilities that I've described. Full visibility, full control. People will also look at their network and decide if there's a critical asset or if there's a problematic area where they're having network issues and upgrade those. If you happen to have legacy switches or traditional switches, any device that's speaking east-west below it, unfortunately, since it doesn't go through an SDN switch, we don't have a lot of ability to control or any visibility into it. However, if you have devices that are speaking east-west, but it happens to go through the distribution switch, we do have visibility and control of everything that passes through the SDN switch. And so there are options here. So you can micro-segment as much of the network as you want or segment it. If you have VLANs that are down in this section of the network here, that's fine. We will pass that. We don't need it. We'll pass it, access control lists, all of those sort of things. We support, spanning tree protocols, things like that. That all will work. As I said, we've spent a lot of effort and time putting into working into a hybrid network. Now we'll pivot. We'll pivot to cybersecurity. And there are two major standards in the US that we see the most, 62443 and NERC-CIP. NERC-CIP much more around energy, but both of them have a concept around segmentation, and our controller provides micro-segmentation, which is actually above and beyond what those require. Network visibility, every device communicating on an SDN network is visible. Both of those standards require that. And then change management. Every change that happens on the network is logged. You can export all of those logs and anything within our software out to a file that you can use in your change management software if you are in an industry that requires that. So we've done a lot that we can do to support these various standards. Typical cybersecurity attacks. These are the most common attack vectors. Phishing attacks, where somebody goes in and tries to steal credentials. Once they're in there, they land and expand. USB drives, and this isn't as dramatic as what happened in Iran, where they had USB drives that were infected. This is much more commonly, I've plugged a USB drive into my personal computer to move a file to something in production. That USB drive picks up a virus from my computer and brings it into production. Misconfigured firewalls happen all the time. Communications or production's down, and you just put some rules in there that just allow stuff to pass through. Static public ports, we see this a lot. I don't have access to a part of my network, so I throw a cellular modem on there. If you go on to Shodan and you look up Allen Bradley, which is the Rockwell brand name, if you're not familiar, there's about 7,000 static ports that are out there that it finds. And so there's a lot of OT devices there that are that way, and those are just waiting to be attacked. But if you properly create your rules, we harden your attack surface, we prevent these attacks from spreading. So on the left, if you have somebody in finance that got phished and they have an infected computer, just by nature of how we set up our rules and deny by default, it cannot get into the OT network. And the access that it tries to do is logged and it's put back in the controller. If you have on the right side a SCADA system that gets infected, it might be able to get to the PLC because it needs to talk to it, but it can't spread throughout the network. You're limiting your blast zone. All of these attempts are logged, and then any of those changes or attempted changes are reportable. We have a northbound API that if you have other software that you're using, so if you've got an SOC or something like that, or other tool, all of those changes or attempted changes are logged and are available via that API. So we can fully integrate into a SOC or whatever other tools you might be using to do that. So that is the longest part of the presentation. So I'm gonna flip over to the software. So just give me a moment, please. Carly, are there any questions that came in while I've been prattling along, so to speak?
No. Nope,
okay.
No questions.
I am just that good.
That's right.
That's exactly what it is. So, okay. So wow, I didn't realize we had so many people. That's great. So this is the software product. It is completely configured and run through a browser. So you can see I'm just running on Chrome here. I have a local version of it. It is most typically run on the the virtualization stack at a customer. You can run it on a bare metal PC if you like. It comes out as an ISO that you install. Some of the most common questions we get is we sell this by how many endpoints that you are protecting or a part of your network. There is an enterprise level tool that includes the API and some other features, but essentially is how many endpoints are in your network and how big is your network. That's how it is typically priced. So in this example, yes.
Hey, Jason, there is a question that just came
Sure.
in. Can you explain east, west, north, south, like what you mean by that?
Oh, okay. So east-west, this is not a great diagram for this is all going to be east-west. East-west is when two peer devices, so we've got an HMI and a PLC, want to communicate to each other. So east-west is sort of side to side. North-south is when this PLC, for instance, wants to talk to like a historian that's higher up in the organization, or some IT asset actually. So if you've got a production management system or an MES or something like that that needs to give commands to the HMI and the PLC, that's what we refer to as north-south communication. Hopefully that clears it up for people. East-west tends to be through a single switch and back and forth. I mean, it can be, I'm simplifying. North-south tends to move to other layers of the organization. Actually, that's a good example here. So this is a Purdue-like model that we put in our software. And this is another way of organizing how devices can communicate. So in this example, there might be two PLCs or a PLC and an HMI that communicate and they stay in this level. That's a good example of east-west communication. Whereas if you've got a SCADA system trying to talk to an appliance up here or some MES system, that's north-south. And like I said, these are just generalized terms to kind of get it across. There's a lot of subtlety, and it's sort of a shorthand to talk about how things are doing. It's not hard and fast rules. So, but in this particular example, we have a bunch of different devices which we've categorized. I'm going to go back to the topology to show this. In this example that I have here, it's a simplified beverage line. Like I said, it's just a simulator of the network, but we have categorized in here PLCs and HMIs for various parts of the network. And once we've categorized these devices, and some devices will automatically categorize, some devices are just so old, there's no way for us to get more information on them. But so if you've got a PLC or an HMI or a motor starter that's on Ethernet IP, we will automatically get that information about it and build it into our network. But if I go back down to level management here, you'll see that I've got a PLC here and an HMI here. These fall into the various levels. A lot of people like to organize business administration, a demilitarized zone, visualization, control, and industrial. Those are sort of basic levels. And we categorize these, and you can move these around however you like. If you don't like that a relay is up there, we can drop it down. It doesn't matter. What matters are these check boxes. And the check boxes say which are these allowed to communicate with. So I've got a smart overload here. There's really no reason that it needs to come back up here and talk to a firewall or a concentrator, or if I've got a historian up here. There's no reason for that. And so we can limit the communication to this level and the one above it. The PLCs and the control level, one above and below. And so, and here it might go all the way to the top and down one level. Once we go back to the network topology, I can actually click on showing the violations of it. Right now, there are none because these are all just PLCs and HMIs, but it would actually show you if you violated any of those rules so that you could take a look at it. You're allowed to override it, but it allows you to figure out, well, maybe these two things shouldn't be talking to each other, and I can change the rules around that. So I digressed a little bit. Back to the network topology here, and I'll go probably another 5 minutes, and then we'll open it up for questions. I want to be mindful of time, but all the devices are here. The switches that we have here are in the center. If I am interested in what's connected to a switch, I can click on the individual switch. I can see which devices are on which port. I can look at what the peer switch peers are. I can get information about the switch. I can click on a device. I can see all the information about the device, what switch it's attached to, what port it's on that switch, and a lot of information about who it's talking to. I did a ping all, and I did put it in learning mode. So all these devices are allowed to ping each other. And that's just sort of the rules I set up here. And I'll get into, I'll show you that in a minute, but I can see what path between two devices. I can have multiple views. I can move parts of the view around if I want to. I can grab and move whole sections of the view around. I've got a lot of options here. I can organize devices into various zones. I've got, in this example, a wet zone and a packaging zone. And if I come in here and I click on the device management, I can look at all the devices in the packaging zone versus the wet zone. This allows me to create rules that are zone specific and simplify things. I can create rules that are device to device. So if I want any of these devices to talk to each other, or I can say, I want anything in the packaging zone to work on, we'll use Modbus this time. I've been using Ethernet IP a lot. I allow all that communication. I'm going to put it in the default policy. I could put it in another policy if I wanted to. And I hit save. And now I can review that change. I have to apply it. So there's always a review process on the changes. And now I have a rule in there that allows me to have any communication within that packaging zone along Modbus TCP. I can also do it on individual devices or types of devices if I want all PLCs to be able to talk to each other. There's a lot of flexibility. Under the switches, I can see all the switches. I can see information about their ports. It's querying them right now. All their ports, what's going on with it, who they're talking to. There's a lot of information that I can get here. And I'm going to go relatively quickly here. I have a dashboard where I can see which devices are communicating the most, which rules are using the most bandwidth. I can also, as there's more bandwidth, since I'm just pinging, that I'm not using a lot of bandwidth, there's a chart at the bottom that'll start showing which switches are being used the most. So you can start to really do some diagnostics on your network, see where problems are happening, chase them down, that sort of a thing. I'm going to show you a really quick example, and I'm going to have to I apologize, I've got a switch screen, so I'm going to do a little screen switching, which will take me a moment, but I'm going to show you I've got this allow protocol rule. And so let me quick switch over to my mini-net, which is my demo screen. And oops, not what I wanted. Well, that's not going to work. Let's do it this way. So over here, we've got Mininet, and you see if I hit ping all on this Mininet, every single packet gets through there. 90 cent, 0% dropped all the way through there. So now let's quick swing over to the controller again. And I can come in here and I can take this from an allow rule to a block rule. And I hit save, and I want to apply it. So now this is available. So we switch back over again to Mininet. And now when I do a ping all, it's going to stop because this particular device is no longer allowed to ping with the other device. The H is the hosts, and that's the devices within there. But you see the X, and now you see that 9 is trying to get to 3 because it was trying to do, it's bidirectional, and it's going to fail over in just a minute. And you'll see that now 2 of those pings failed. So we can very easily deny traffic. The only traffic that we allow is ARP traffic because that's sort of the heartbeat of the network, but any other protocol we can stop. So let me back into the product, and I've just got a couple more things to show you in the product, and then we'll go back to the PowerPoint and wrap with questions. There's just a couple other things. One is we have the ability to create change sets. So if you need an approval process for rules, say you want to allow a certain subset of your users to create rules, but you don't want them implemented until they're validated and approved by another set of users, we have the ability to do that. We also have the ability to create schedules for these rules, or for policies really, so groups of rules where you can turn them on and off. For example, if you have a vendor wants to be able to do maintenance on their machine or diagnostics or something like that, you can say, yes, but you only can do that when we're not in production during third shift. And you can only allow access for them during third shift. Another example is if you've got an engineer coming on site and you want to give them 2 weeks worth of access, you can do that with a scheduler as well. And so that's the majority of the product. Jeff Smith and I joke that if we can't make you dangerous in our product in 15 minutes, we haven't done our job. And so let me switch back over to the main screen here. And then we'll go back to the PowerPoint. Just kind of wrap up here. So what you get a single place to manage your entire network. Complete control over your network of all the SDN pieces that are on there. Every device communicating on your network is visible to you. The network is denied by default by not just endpoints, but also communication protocol. So you've got a microsegmented network, and we've got a very reliable network that we're proactive about, so you don't have to manage a lot of the things that cause downtime. So my question to you is, which one do you want running your network? That Ford Taurus from year 2000 or something super modern with a lot of really cool electronics in it?